I welcome all of you to the class, and today we are going to start our lecture, our lecture series. In lecture 1, we introduced you to the course contents, and today is our lecture 2. And lecture 2 is actually the lecture from where we'll be starting now the course contents. So today we have lecture 2, lecture number 2. Just a minute. So we start with the today is our lecture number 2. Today is our lecture number 2. Today we will be starting from the study of a physical quantity called stress. Today we will introduce what do we mean by stress. And introduction to the stress is what is our unit 1, or I can call this as this is our chapter number 1. Introduction to stress is our chapter 1, and we can also call that this is unit 1 of our syllabus. As far as the stress is concerned, we know the machine elements, whatever be the machine elements are subjected to loads. The machine elements are subjected to loads. What do we mean by saying the machine elements are subjected to loads? We mean whatever be the machine element in hand, the main job of the machine element is to withstand the load, is to carry the load. Okay, this is true for machine element as well as for what we call as the structural elements, or we call them as structural members. Structural members or machine elements have to withstand the load. For example, in structural members, we talk of beams. Let me take an example of beams. Beams are structural elements which are subjected to loads. For example, this is what we call as a cantilever beam. This is called a cantilever beam. And this cantilever beam, like other beams, is subjected to loads in a direction perpendicular to its axis. As far as the axis of the beam is concerned, the axis of the beam is this is the axis of the beam. Okay, but as far as the loads are concerned, the loads on the beam will be in this direction. Okay, the load on the beam will be in this direction. The load may be a uniformly distributed load, or it may be a point load. Okay, it can be anything. It can be a uniformly distributed load, or it can certainly be a point load. It can be anything. But the important thing is that as far as the direction of the load is concerned, the load and the axis, this is the axis of this beam, there is an angle between the axis of the beam and the load. Okay, so as far as this beam is concerned, this beam we often see in our houses, its function is to withstand the load above. Okay, uh, in the same way, let me suppose we have a slab. Okay, let me suppose we have a slab like this, or let me redo it. Here we have a slab. Okay, and this slab is uh, subjected to loads, and the loads on the slab are in this direction. Okay, it has loads in the downward direction. Loads are in this direction. Okay, so as far as the slab is concerned, if the loads are acting in the downward direction, this slab should have the tendency of withstanding these loads. Okay, slab should have the tendency of withstanding these loads. It means the slab needs to be supported. Okay, it should have supports. Okay, there should be supports that can withstand the loads, Okay, So as far as the supports are concerned, the supports will be in this direction. Okay, so this slab is to be supported, okay, so that it can withstand the loads above, over it. These loads will try to move this portion in the downward direction. Okay, so for this slab to withstand the effect of these loads, it needs to be supported. So it will have supports from the bottom side. Okay, so as far as the stress is concerned, in order to define the stress, let me talk about a machine element. Let's suppose we have a prismatic bar. Let's suppose we have a prismatic bar. Okay, let's suppose its area of cross section is everywhere uniform, let me suppose, and its area of cross section is, say for example, A. Okay, the length of this bar is, say for example, the length of this bar is, say for example, L. Okay, this bar is free at one end, it's free at one end, and the bar is fixed at another end. The bar is fixed at another end. Okay, now what we do, let's locate the axis of the bar. Let me say the axis of the bar is, this is the axis of the bar. Okay, this is the axis of the bar, the central line of this bar. Fine, and this bar is subjected to a load in the direction of this axis, and load we are starting from here, and this load is being applied in this direction. Force, what I mean to say, load or force, they are the same thing, interchangeably used. Let me call the load as, or the force I represent by F, or I represent this force by P, one at the same thing. Okay, so what we have a bar of length L, area of cross section A, fixed at one end, free at one end. Okay, subjected to load or force F or P at one of its free end. Okay, the force is applied in such a way that this force is in the same direction as the axis of this, bar. Okay, so we have a bar, the force is applied in the same direction as the axis of this bar. Okay, so what we do, after some time the equilibrium will be established. The equilibrium will be established. By saying that equilibrium will be established, it means that the bar is at rest. The bar neither moves along positive x-axis, neither moves in this direction, nor the bar moves in this direction. Okay, so if the bar happens to be in equilibrium, or in other words, we can say, as this bar is subjected to force P along x-axis along this direction, so what happens, the bar has the tendency of opposing the effect of the external force. We call this force F, we call this as external force. We call this as external force, or we call this as external deforming force. This is not only external force, this is external deforming force. Why this is external deforming force? Because this force is trying to deform your machine element. Okay, the bar is having length L. As we apply force F on this bar, the length of the bar will change, the area of the bar will change. So it means the force F that's being applied at the free end is nothing, it's simply a deforming force. It's trying to deform our machine element. Fine, now in response to the external deforming force, the machine element sets up what we call as the internal restoring force. It sets up the internal restoring force. Internal restoring force. This is the property of every machine element. This is the property of materials. Okay, that is, once you try to deform them, you apply the external deforming force. The machine elements try to create internal forces that try to restore the machine element back to their original configuration. And I'm repeating it. As we subject a machine element to external deforming force, the property of the machine element, the material of the machine element is such that it sets up the internal restoring force that tends to restore the machine element back to its original configuration. Okay, it tries to restore the machine element back to its original configuration. This is called internal restoring force. What we will be doing, Let's take out a section. Let's draw a section over here. Let's cut out a section here. Let's take a section here. So this section is now dividing this machine element into two parts, the left part and the right part. If left part and the right part are in equilibrium with each other, if this portion and this portion are in equilibrium, that means at this area of cross section, the resultant of all the forces has to be equal to 0. What I mean to say is, let me isolate this portion. Okay, let me isolate this portion. As I'm isolating this portion comes out as a piece like this. Okay, comes out at a piece like this. Fine. It will have force F or load P acting in this direction. But this, once you are taking this section out, this section is an equilibrium. Fine. But if you look at this section out here, it is not in equilibrium right now because this force F will try to move the machine element in this direction. So this will not be in equilibrium. For this machine element to, for this portion to be in the same equilibrium as it's here, what is has to be there? There has to be the force in the opposite direction that we call as F prime, such that F has to be equal to F prime. Now the question is, we know this F is the external deforming force. It's trying to deform the machine element. Now once we are taking this section out, okay, and we're applying the same external deforming force F on the machine element, this portion of the machine element loses its equilibrium. Now in order to make it, in order to set equilibrium in it as it was originally when it was portion of the bar, there has to be force F on this bar in the direction opposite to that of F, but with the same magnitude as that of F, for this to be at equilibrium. Now the question is, who is setting up this force F prime? Okay, this force F prime is being set by this portion of the machine element. Okay, this force F prime is being set, this force F prime is being set, okay, by the left portion, by this portion of the machine element on this portion. Okay, this force F prime, this is nothing, this is internal restoring force. This is internal restoring, this is internal restoring force. Fine. This is internal restoring force. The tendency of this force F prime is to nullify the effect of the force F. Okay, force F tries to deform the machine element, but force F prime is trying to restore the machine element back to its configuration. Okay, this internal restoring force F prime divided by the area, that is A, is what we call as the stress. This is what we call as the stress. This internal force, internal restoring force per unit area of the machine element where it's acting, this internal force per unit area, this is called stress. Fine. Now, if you look at F prime, we said that F prime is equal to F. So we can also write this as stress. Stress is equal F by A. Stress is equal F by A. Now, if you look at force, the unit of force is Newton. The unit of area in meter is meter square. So Newton per meter square is the unit of this stress. And we know Newton per meter square is also called Pascal. Okay, so Newton per meter square or Pascal is the unit of this stress. Fine. If I again clarify what I have been saying right now, I said that stress is equal force per unit area, restoring force per unit area. Okay, its units are Newton per meter square. Okay, what's also called as Pascal. Fine. Area is also measured in mm. Okay, area is also measured in mm. Okay, so the unit of this area is not only meter, it's also measured in mm square, millimeter square. Okay, and we know as far as 1 meter is concerned, it's equal 10 raised power 3 mm, or 1 mm is equal 10 raised to power minus 3 meter. Fine. So it means if I write this stress in terms of Pascal, we are writing this as Newton per meter square. And if we represent this area in terms of mm, then it will be Newton per. Now this 1 meter is equal 10 raised power minus 3. This is equal 10 raised power, this is meter square. This is 1 meter is 10 raised power 3 mm. So we can write this as this is 10 raised power 3 mm, and we have square over it. Fine, because 10 raised power 3 mm is equal to 1 meter. That's equal Newton per 10 raised power 6 mm square is equal to 1 Pascal. That's equal, we can say, we can therefore say 1 Newton per mm square is equal 10 raised to power 6 Pascal. When you cross multiply it, that's equal 10 raised to power 6 Newton per meter square, because 1 Pascal is 1 Newton per meter square. So we got the important relationship, that is 1 Newton per mm square, 1 Newton per mm square is equal 10 raised to power 6 Newton per meter square. 10 raised to power 6 we call as mega, and Newton per meter square we call as Pascal. So we can simply write 1 Newton per mm square, or let me change the color. We can therefore say 1 Newton per mm square is equal megapascal. It's written like this: capital M, capital P, and small a. So this is the relationship between the stress expressed in mm and between the stress expressed in the Newton per meter square. So 1 Newton per mm square is equal to 1 megapascal. Okay, this is the unit of stress. Now we return back to what we have done. So we had a machine element. Let me redraw this. This was our machine element. Its area of cross section was, say, for example, A. Okay, its area of cross section was A. The length of this machine element was L. Okay, and this machine element was subjected to load F or P in Newton. Fine, and it was fixed at one end. Machine element was fixed at one end. Fine, it was fixed here. Okay, so we took a section like this. We had taken a section like this. Fine, and we said on this section, the force was acting in this direction. The force continues to be in the same direction. Okay, this was the direction of the force. And on this section, okay, sorry, on this section, this one, this area that we expressed, its area is again A. Okay, the stress was equal F by A. Fine. Now let me introduce a few more things to you. Once you are representing stress, the stress is to be represented on some area. Okay, and first of all, the point where you have to calculate or express the stress, around that point you have to express an area. You have to draw an area around that point. For example, in case of this machine element, if I ask you what is the stress on this area, for example, okay, first of all you calculate the force acting on this area, that is F. Okay, and also express this area A in terms of area vector. express this area in terms of area vector. What do we mean by saying? By saying, let me redraw my diagrams for some time to make it uh, more. For example, let me take the machine element again. Let me redraw my machine element. Okay, so this was our machine element. Okay, and okay, it's fixed here. So let me not draw it, or let me close it here. This is fixed here. Fine, and closing down. Now here, suppose where this is the axis of this beam. Sorry, I suppose the axis of the beam. So this is the axis of the beam. Axis of this bar, and we're also applying force in the same direction. I'm asking you, the force F is being applied. Now we are asked to calculate how much is the stress on this area. In order to calculate stress on the area, first of all, what you do, calculate the magnitude of this area. Say the magnitude of the area is A. Fine. This is the step number one. So we have to calculate how much is the stress acting on this face. Okay. How much is the stress acting on this face or area? So first of all, what we do, we find the magnitude of this area. That is A. Fine. Then, so first step will be calculate calculate magnitude of area. Once you have calculated the magnitude of area, second will be draw unit vector. Draw unit vector to the area. What do you mean by drawing unit vector to the area is, I mean to say is drawing unit vector to the area is, on this area, you have to draw a unit vector in such a way, that is perpendicular to this area. Okay. So if I draw a unit vector to this area, I can draw a unit vector like this. Magnitude of this vector is 1. Or I can also draw a unit vector like this. We can also draw a unit vector like this, perpendicular to the area. Both ways. So if what we have to do after calculating the magnitude of area, what we have to do, we have to draw the unit vector. Now the question is, how do we draw the unit vector? The unit vector is to be drawn, perpendicular to the area. It's to be drawn perpendicular to the area, surface of the area. Okay. So if you look here, if we have to draw a perpendicular to this area, we can draw a perpendicular to this area in this direction, or we can draw perpendicular to this area in this direction. Now, which of the two directions is correct? You have to draw the directions in such a way, such that if you assume that you have a screw here, you assume that you have a screw on the surface. Okay. As you rotate the screw, the screw should come out of the surface. Okay. I mean to say, you have to draw the unit vector to the area in such a way, such that if you have a screw on the surface of the area and you rotate the screw should come in the same direction as the direction of the unit normal. That is, the screw should come out of the surface, not go into the surface. Okay. So if you have a screw here and you rotate the screw, if the screw has to come out of the surface, then the motion of the screw has to be in this direction. Therefore, this will be the direction of our unit normal, and we represent unit normal by n cap. Okay. So first of all, what we have to do, the area where we have to calculate the stress, we have to calculate the magnitude of the area, which we have done. Then we have to draw an unit normal to the area. That's what we are doing. And the third step is find the magnitude find the magnitude and direction, find the magnitude and direction of force F. Find the magnitude and direction of force F. Okay, the force F happens to be in this direction. Fine. And if we represent, if we call this to be our x-axis, we call this to be our y-axis. Okay. So once we are taking care of these three steps, the phase where we have to calculate the stress, the area where we have to calculate the stress, what we are doing, we are calculating the magnitude of the area. We are drawing a unit normal to the area. Fine. And also we are calculating the magnitude and direction of the force. Fine. Then we define, let me write here, then we define stress. Then we can define, we define stress now. We define the stress as stress, S-T-R-E-S-S, stress, okay, is equal to, first of all, write down the force. We write force F. Force F. On which area is this force acting? It's acting on an area whose magnitude is A. Okay. And on which the unit vector is n cap. Fine. So we write stress is equal force acting on area A whose unit vector is drawn n cap divided by the magnitude of area, that is A. Fine. Don't please cancel this area and this area. These two cannot be cancelled because the area that we are expressing in the numerator here, okay, it is not in multiplication of F. It's not in multiplication of, this is symbolically used. Symbolically used, this is used to represent the stress. Okay, we are writing it as force F acting on an area A whose unit vector is n cap divided by the magnitude of area A. Okay, so this area and this area is not in product of this F. This is used to denote the force on the area over which it is acting, nothing else. Okay, so what we can further modify this as, we can further modify this as, that's equal force F acting on an area A whose unit vector is n cap. And if you look at this n cap, this is a unit vector along x-axis. This is a unit vector along x-axis. We can write this as I cap divided by the area A. Fine. We can further modify this as, can further modify this as, we can further modify this as, look here. As far as force is concerned, the magnitude of the force is F. And what is the direction of this force? The force is acting in the same direction as your x-axis. So we can write this as Fi cap. You can also write this as Fi cap. It's acting, so force of magnitude F is acting along x-axis. Fine. On an area A whose unit vector is also along x-axis, Ai cap, divided by A. Okay, so we write this as stress. And if you look, your force is acting along x-axis. Okay, your area is also acting along x-axis. Okay, so we say as far as the stress is concerned, this stress is acting in x-axis. This stress is acting along x-axis. Okay, or we can say this stress is acting on a face. Okay, this stress is acting on a face which is in the same direction as the direction of your force. What is the direction of your area vector? The direction of the area vector is along x-axis. What is the direction of your force vector? The force vector is also acting along x-axis. Fine. When you have stress acting on the face in which the force and the area vector are along the same direction, we call that stress as normal stress. We call this as normal stress. This is one thing. And the most important thing is, in order to express this normal stress or any other stress, you require two vectors. Okay, in the formula of the normal stress or shear stress, which we'll just study, you require two vectors. First of all, you require the direction of the force. You require the magnitude and the direction of the area over which it is acting. Okay, that's why this is very different from a vector quantity. A vector quantity is a quantity which requires magnitude and direction to express itself. But here, stress is a physical quantity which is dependent upon two vector quantities. You require two vector quantities to express the stress. Therefore, we say stress is a tensor. We call it as a tensor quantity. Though I will be taking up tensor in good detail uh, in your study of introduction to the Cartesian tensors. In the study of Cartesian tensors, I will be talking about tensors in good detail. But this is something that we came across in this lecture. And what we came across in this lecture is force acting on any area. In order to express the force acting on an area, we require the magnitude and direction of the force. We require the magnitude and direction of the area. Okay, so we require two vectors, the two vector expression. So in order to express the stress, you require the magnitude of the force and direction of force. You require the magnitude of the area and the direction of the area, and then only we can calculate the stress. And this stress, we call this as normal stress. Okay, we call this stress as normal stress. Okay, let's go ahead. Let me redraw my area element right now. Let me suppose we have a machine element like this. Let's suppose we have a machine element. Okay, fixed at one end and subjected to force F at its free end as we had previously. Okay, initially in the previous case we calculated stress on this face, and we said stress on this face, which we call as normal stress, which is represented by the term sigma. Sigma represents normal stress, which is given by F by A. Okay, and in more detail we write this as F I cap acting on an area A I cap divided by A. This is normal stress. Okay, where the force and the area, where the force vector and the area vector are along the same direction. Our force vector is along this direction, our area vector is along the same direction. The stress that this force creates is called the normal stress. Fine, since the expression of the stress depends upon two vectors, this we call this as the tensor. We call this as tensor. Fine, I am repeating that I will discuss the tensors in detail once we discuss the mathematics of the solid mechanics. Then we can talk about the Cartesian tensors. But here, just we need to remember that expression of stress does require two physical requires two vectors. Okay. Anyways, if now we have a problem, and say for example we are given an area, we are asked to calculate the stress. Say for example on this area, the area is now slanted. Say, for example, someone takes an area like this, and we are asked to calculate. Say, for example, now we have an area like this. Okay, we have a slanted area. Fine. If we have a slanted area, okay, now we are asked to calculate how much is the stress on this area. How much is the stress on this area? If you look at the line of action of the force is still acting in the same direction. The force is acting in this direction. Okay. Now we have to calculate this area. Well, sorry, we have to calculate how much is the force acting on this slanted area. Okay. Now, in order to calculate, so if you look in two dimensions, this area will essentially be like this. It will be like this in two dimensions. Fine. It will be like this. Okay. And the perpendicular area is like this. Fine. Let me instead of drawing these areas like this, we draw them with the help of line. Okay, otherwise they are areas. Fine. So let me redraw it. So we have a problem in hand. We have to calculate, or let me draw it here. we have to calculate the stress acting on the inclined plane. Let me express it. We have a slanted plane. Okay, fine. Now force is acting in this direction. This is force F. Okay, we are asked to calculate how much is the force acting on this inclined plane. Okay, so what we will be doing, first of all calculate the area over which you have to calculate the stress. Fine. You have the cross sectional area which I am representing in the form of line. The cross sectional area is A. The cross sectional area is A. I should know how much is this area. Let me call this as A prime. Fine. Let me say that this slanted area, which is not certainly equal to this area, cross-sectional area, let me call this as A prime. So the area of the plane where I have to calculate the stress is A prime. Fine. Then second thing I have to do is to draw the unit normal. Okay. How do I draw the unit normal? I said the normal, unit vector. How do I draw the unit vector? I said the unit vector should be perpendicular to the area. So the unit normal will certainly be in this direction. This is the direction of the unit normal. Okay. Let me call this unit normal as n cap. This unit normal to this area has to be perpendicular to the area. This angle has to be 90 degrees. That's what we are doing. Okay. Now let me call this angle as angle theta. Let's call this angle as angle theta. Fine. So this angle, we are representing this angle to be the angle theta. Okay. So if you look at this angle, this total angle is 90 degree. This total angle is 90 degree. Therefore, this small angle will be 90 minus theta. Fine. Since this angle and this angle as are alternate angles, this angle will also be equal. This angle will be also equal 90 minus theta. Now in this right angle triangle, this angle is 90, this angle is 90 minus theta. Therefore, this angle has to be equal. This angle will be equal theta. Fine. So this angle is theta. This total angle is 90. This angle is 90 minus theta. This angle and this angle are alternate angles. Therefore, this angle will also be 90 minus theta. This angle is 90 minus theta. This angle is 90. Therefore, this angle will be equal theta. Fine. Therefore, we can draw this diagram properly here. We can write this as, we can write this diagram as, this is our slanted area. Fine. We are having force F acting in this direction. We are having a unit normal to the area in this direction. Fine. This angle is theta. And this angle is also theta. While as this area is A and this area is A prime. Fine. Can we write in this right angle triangle? Let me call this as right angle triangle 1, 2, 3. In right angle triangle 1, 2, 3, can we write as cos theta is equal to base by hypotenuse, that is A by A prime. Therefore, A prime is equal to A by cos theta. Therefore, that is A secant theta. This is the relationship between A prime and A. Okay, so A prime, the new slanted area, is A times the original cross section times the secant theta. Fine. Now this F that we have, this F can be, we can do one thing. This F we can resolve in two components. Okay, one component will be in this direction. One component of F will be in this direction. Okay, in the same direction as the direction of the unit normal. And another component will be in this direction. Sorry. in this direction. Okay, so the f that we have, this f we have resolved into two components. One component is along the unit normal, that is f cos theta, and another component is parallel to the area of cross section. We call this component as f sine theta. Fine. So the f that is acting on the inclined area, slanted area, it's having two components. This is f cos theta and f sine theta. This f cos theta is perpendicular to slanted area a prime. Fine. And this f sine theta is parallel to slanted area a prime. Fine. Okay. Now let's discuss the stress created by f cos theta. Okay. Therefore, stress created by f cos theta. Look at f cos theta. F cos theta creates stress on the area such that your area unit normal to the area and f cos theta are in the same direction. And I said previously, when the force and the area vector are in the same direction, then the stress created is a normal stress. Fine. Therefore, this f cos theta creates normal stress. It creates normal stress. Let me clear some space first. It creates the normal stress. And we can write this as sigma. And sigma is created by which component? F cos theta component. Fine. And the magnitude of this normal stress will be equal to force, that is F cos theta, divided by the area, that is A prime. Fine. That can further be written as, maximize, that can further be written as F cos theta divided by A prime. Our A prime is A by cos theta. A by cos theta. That is sigma normal stress on the inclined plane becomes equal F by A cos theta is cos square theta. Fine. Cos theta multiplied by cos theta becomes equal cos square theta. Fine. We can further write this as, we know cos square theta is, we can further write this as sigma, and I will write the sigma as sigma on an inclined plane. I will write this as sigma theta. Why I'm writing this as sigma theta? Because this is stress acting on this inclined plane. Okay, fine. So sigma theta, normal stress on the inclined plane, is F by A, and your cos square theta is 1 by 2, 1 plus 1 plus cos 2 theta divided by 2. Okay, so this is the normal stress acting on the inclined plane, that is F by A, 1 plus cos 2 theta divided by 2. Now look at this F by A. What was this F by A? This F by A was the stress that was acting on this perpendicular area, on this area. Okay, this is F by A. So I can write this as sigma theta is equal to sigma by 2 multiplied by 1 plus cos 2 theta. This is one thing. Fine. Now let's calculate the stress which is created by this F sine theta. Fine. Now when I went on to calculate the stress because of this F sine theta, the stress is created will be, the stress because of this F sine theta will be, stress because of F sine theta will be equal force, that is F sine theta divided by the area, that is A prime, that is equal F by A, that's equal to F sine theta divided by A prime, that is A by cos theta. That can further be written as F by A sine theta cos theta. Fine. That can further be written as, if we multiply and divide by 2, we can write this as twice, or we can write this as f by 2a 2 sine theta cos theta. Fine. And we can write this as this is f by 2a, and this 2 sine theta cos theta can be written as sine 2 theta. This is sine 2 theta. Now look, what we'll be calling this stress as? This stress we call as normal stress. Now look here. This is stress created by the force. Okay. This is stress created by the force, such that the force and the area are now perpendicular. Your force vector is in this direction. F sine theta is in this direction. Okay. We are calculating stress created by F sine theta, that is in this direction. Okay. While as we are calculating this stress acting on an area whose unit normal is in this direction. The angle between force and area is 90 degree. When you are calculating stress on an area such that the angle between the force and the area vector is 90 degree, that stress is called shear stress. That stress is called shear stress. And we represent shear stress by tau. Since this shear stress is calculated on an inclined plane, we write this as tau theta. Fine. And look at this f by a. This f by a is equal, this f by a is equal to what? This f by a is equal to sigma. So we can write this as sigma by 2 sine 2 theta is equal to shear stress tau theta. So we have two formulas now. We have tau theta is equal to sigma by 2 sine 2 theta, and the normal stress acting on the inclined plane is sigma by 2 1 plus cos 2 theta. Okay. Now from here, what we have to do, we have to understand the concept of the shear stress. Fine. And then from these two formulas, the variation of the normal stress and the shear stress across the planes of this machine element. So we have now two problems in hand. First of all, understanding the concept of the shear stress again, and the variation of the normal stress and the shear stress across this machine element. That we shall be doing hopefully in the next class. Thank you very much.